Now I'm going to move on to talk about Gaussian processes. And these can be thought of as Bayesian kernel machines. And the subtitle of this lecture is Why I Don't Use SVMs. Okay? And let me just reveal, it's not that I don't use SVMs because I think they're a bad thing to do. SVMs are great and they're very powerful. But basically anything you can do with an SVM, you can do with the Gaussian process. And the Gaussian process is a fully probabilistic model, so I'm much more comfortable just doing things with Gaussian processes instead of SVMs. So I will explain that in more detail in a few slides. But let's talk a little bit about a very simple and important problem. This is nonlinear regression. So imagine you want to learn a function. Let's call the function f, which is represented in blue here. You want to learn that function with some error bars. So you want to know how uncertain you are in the function and to get some predictions. From data, which are these magenta dots, the data are pairs of x's and y's. Okay? So it's a function mapping from x to y. Now, a Gaussian process is a general way of learning these functions. So I showed you examples with polynomials, but polynomials are very unnatural in some ways because, as I mentioned before, almost no real-world phenomena are really captured by some polynomial. Like, for example, if I measure, let's say, height as a function of age for people, okay? Height is roughly a function of age. It's quite a noisy function of age. If you tell me somebody's age when they're a child, their height goes up, and then it maybe plateaus and maybe goes down at the end a little bit, right? So that function is not really a polynomial. Nobody could reasonably argue that it's a polynomial. And a Gaussian process is meant to be just a very flexible way of learning unknown functions from data. So Gaussian process defines a distribution over functions which can be used for Bayesian regression. The basic idea is you define your distribution over functions, and then you observe some data, and then you take that distribution over functions, you multiply it by the likelihood, you renormalize, and you get a new distribution over functions given the data. Now that sounds complicated because functions are infinite dimensional objects. But as we'll see, it's actually not very hard to work with Gaussian processes. So to be a little more precise, Gaussian process defines a distribution over functions. Let's say f is a function mapping from some input space x to the reals, like this. And it's infinite dimensional if x itself is the reals. If x is a discrete space, it could be a finite dimensional function. Okay? Now, let this symbol here, this bold vector f, denote the function f evaluated at n data points. Okay, so now, whereas f is an infinite dimensional object, this bold f is a vector. It's an n by 1 vector. Okay? Now, if you have a distribution over the function, then when you evaluate the function at n points, you have a distribution over this n-dimensional vector. And the definition of a Gaussian process is that the distribution is a Gaussian process if for any finite subset of the input space, the marginal distribution over that finite subset, P of this bold vector f has a multivariate Gaussian distribution. Okay? So what does that mean? It's a distribution over functions. If you evaluate it at a few points and you string those together into a vector, then you always get a Gaussian vector coming out. So let's try to get some intuition about that. So that's just the definition from before. And just like the multivariate Gaussian, the Gaussian process is parameterized by a mean and a covariance. So let me just so univariate Gaussian, we all know, has a mean, mu, and a variance sigma squared. The multivariate Gaussian has a mean vector, mu, and a covariance matrix, sigma. And the Gaussian process has a mean function, mu, and a covariance function, let's just call it k. K for kernel is a function that takes two arguments. In this case, it's a matrix. In this case, it's a scalar. And all of these are related to each other. The Gaussian process is simply an infinite dimensional generalization of the multivariate Gaussian. And it's a generalization which says if I evaluate the function at some number of points, I get a multivariate Gaussian, in the same sense as a multivariate Gaussian is a generalization of a univariate Gaussian, because if I evaluate any of the single variables, it has a univariate Gaussian distribution. Okay? So these are all the same distribution, basically, but in different dimensions. Now, Gaussian process is parameterized by a mean function and a covariance function or kernel, k. And the basic idea is that the joint distribution of the function evaluated at x and x prime is bivariate normal with mean mu of x prime, and covariance matrix given by taking the kernel k and evaluating it at x and x prime and forming this 2 by 2 matrix. And similarly, for any number of evaluations of the function, mu is an n by 1 vector and sigma is an n by n matrix. Okay? So I think the best way to understand this is maybe through some pictures. I'll get to those in a minute. Okay. So just as a reminder again, Gaussian process is parameterized by a mean function and a covariance function. And the covariance function tells us something about how similar the function values are at a pair of points xi and xj. So here's an example of a covariance function, and the terms in the covariance function tend to be interpretable quantities that define for you properties of the function that you're learning about. Now, once the mean and covariance functions are defined, everything else about the Gaussian process follows from basic rules of probability applied to multivariate Gaussians. So let me just go through this in a little bit more detail, and maybe I'll just do the demo here. Okay, so the demo I'm going to show you is a demo of just generating samples from the Gaussian process. Okay, so let's see. Okay, so what have I done? I've just generated a sample from one function. I've generated one function from a Gaussian process prior. Okay, so remember, the Gaussian process is a distribution on functions, and all I've done is generate one function from it. And this is what the function looks like. It's a function that maps from x. X goes from 0 to 100. Just happens to go from 0 to 100. And then this is f of x plotted here. Okay? Now, what do you see in this function? What can you tell? It's sort of... It's a nice function. It's a nice function. It's kind of smooth. It bumps up and down, right? You know, on average, the function seems to be centered around 0, right? And it varies roughly smoothly. Okay? But you can't really tell much just from one sample. Just like if I said, here is a... Okay, here's something I could say. I could say, I have a bivariate distribution over two variables a and b. And here is one draw from that bivariate distribution. You know, you can't say very much about the distribution just from one draw. But you know, already from one function, you can say a little bit about it. But let me draw another function from this Gaussian process prior. One more. Okay, that's another one. All right. And I'm going to draw another one. Maybe two more. Okay, now I've drawn 4 functions from this Gaussian process prior. Okay, so it's like drawing, you know, 4 points from some distribution. Okay, except each of these points is a whole function. So now what can you tell me about this, this Gaussian process prior? Can you tell me anything reasonable?
See the mean of this.
Yeah, the mean of these functions is roughly around 0, right? And the covariance represents how related the function values are at nearby points. Okay, so if I take location 20 and 21, which are next to each other, the function value at x equals 20 and x equals 21 are highly, highly correlated, right? So actually, I'll draw it here like this. Instead of a and b, I'm going to draw this on this axis. I'm going to draw f at x equals 20. And here is f at x equals 21, right? On average, the function value at x equals 20 is roughly around 0. But at 20 and 21, they're highly correlated. So actually, f at x equals 20 and f at x equals 21 might look something like this. Okay. Let me draw 4 more functions. All right. So this is a distribution over functions. Now I've drawn 8 examples of this distribution over functions. And you know, now it's hard to follow the lines. It's a bit like spaghetti. But you can tell that the function values are highly correlated at nearby points, but far away at, you know, the function value at x equals 20 and the function value at x equals 60 is generally pretty, there's very low correlation, right? So this, what is the covariance function? Well, the covariance function tells us how much the function covaries at 2 different points x. Like x equals 20 and 21, maybe the covariance is very high. At x equals 20 and 60, maybe the covariance falls down to some low value. I mean, I'm not going to go through the detailed form of this covariance function. Okay? And of course, if I draw a lot more functions, then it becomes a bit of a mess. But now if I look at the marginal distribution of the function value at any one location, that marginal is univariate Gaussian. If I look at the marginal at, say, 1, 2, 3 locations, here, here, and here, then that marginal distribution is multivariate Gaussian, 3-dimensional. And for any choice of points on this axis, any finite subset of these points, the marginal distribution is multivariate Gaussian. Okay? Does this make sense to people? Okay? In fact, the way this code is sort of embarrassingly simple. I'm going to stop it, and I'm going to say edit. Most of this is MATLAB. Who uses MATLAB here? Okay. Who doesn't use MATLAB? All right. So most of this is just junk to display things and then decide on the interface and so on, blah, blah, blah. Then I create the covariance function somehow. And then I take this is the Cholesky decomposition of the covariance matrix plus a tiny amount on the diagonal so I don't get singularity. And how do I generate these functions? I generate a bunch of independent Gaussian random variables, and I multiply them by the Cholesky decomposition of the covariance matrix. And that's the general procedure for generating multivariate Gaussians. So all I've done, in fact, in this picture is, in this picture is generate from a 100-dimensional Gaussian and plot it like this. But the covariance matrix of that 100-dimensional Gaussian is such that the functions it generates are going to look smooth when I connect the dots, the 100 dots, to each other. Okay?
Question?
Yes?
The Gaussian is 100-dimensional, right? Is that related to the number of sort of bumps, I would call them, on the graph? Excellent question.
Very good question. The bumps is related to the covariance function that I use. So I'm going to rerun the demo. Okay. Sorry. Okay. So the choices it says is simple Gaussian process demo, which covariance function to use. My choices I've set up are, this is called the squared exponential. The covariance goes down with e to the minus distance between points squared with a length scale of 4. That was the one that I showed. I could do a length scale of 2. I don't know if you remember. Okay. If I do a length scale of 2, the functions are much more wiggly. The length scale in the covariance function is what's telling you how quickly the function goes up and down.
So the function in a certain way provides smoothing for the result, right?
Yes, yes. And here I will draw, in fact, one sample from one sample from a length scale of 4. And now one sample from a length scale of 2. Okay, so the orange one was length scale 4. The red one is length scale 2, so it's more wiggly. And now I'm going to draw one sample from length scale 8. Okay, so the brown one, sorry, all these colors, chooses colors somewhat randomly. The brown function is length scale 8, right, which varies much more slowly. All right. And that's just in how you define this covariance function. And in particular, in this picture here, this R is the length scale. It could be like 2, 4, or 8. This alpha is 2 in all of these examples. Okay. Any other questions about that?
I see that we have infinite number of functions which we can generate through Gaussian process.
Yep.
So if you would draw them all, this infinite number of functions, you would have white noise, yes?
You would have white noise. You wouldn't have white noise because it's there's covariance here. So at any one point you have a Gaussian distribution, but conditioned on that, then the function is smooth. Okay, and we'll see examples of that in a minute.
So for example, if we have this covariance of Gaussian process only on diagonal, then we could have.
If by Gaussian process just has elements on the diagonal, then it would draw things that are white noise. Let me show you some other examples of Gaussian processes. I will, maybe I'll clear these. Okay, so let's just try a different kind of covariance function. This covariance function goes down with e to the minus absolute value of d rather than e to the minus d squared. So what is that called? Does anybody know what that's called? If you know, then you know a lot about Gaussian processes. Okay, let's try that. And I'm going to draw one sample. That's what it looks like. That's one sample from that Gaussian process. Okay. You can draw another sample and another sample. All right. So the colors are a little bit similar now. Okay. So this Gaussian process is a form of Brownian motion. Okay. So this Gaussian process, if you've studied Brownian motion, or it's also sometimes called Ornstein-Uhlenbeck process, it's a Markov process with independent Gaussian increments. So if you zoom in more and more, you'll see that the functions are not smooth at all. They're continuous, but they're not differentiable. Okay? That's also a Gaussian process. And then, in terms of the code, it's basically, one line of difference between these different Gaussian processes. Okay? And I'll draw you another kind of Gaussian process. This has linear covariance function. So what does the sample from that look like? It looks like that. Okay, that's a Gaussian process. Okay? Looks like a line. It's a sample from a Gaussian process. I'll give you a few more lines so you can get a better sense for it. Okay, that's 3 samples from the Gaussian process. Let's do 10 more. Okay, so this is a Gaussian process with a linear covariance function. It's just a special case of Gaussian process. Gives you a distribution on straight lines. The marginal at every point is Gaussian. The covariance between every pair of points is given by the covariance function, and the joint distribution is multivariate Gaussian. Okay, so that's like 30 draws from the linear Gaussian process. Okay, so that's drawing from the prior on Gaussian processes. But really, we're interested in learning about functions from data, right? So let's use a Gaussian process for nonlinear regression. Okay, so here's what we're going to do. We're going to imagine that we have pairs of points xi and yi. And that's our data set. And we have n pairs of such points. We're going to say, instead of saying yi is a polynomial in x plus some noise, we're just going to say that yi is f of x plus some noise, where f is drawn from a Gaussian process with some mean function. Let's say the mean is 0. It doesn't really matter so much what the mean is. The covariance function matters quite a lot, though. let's say f is drawn from a Gaussian process with mean 0 and covariance function k. And let's say that epsilon is Gaussian noise. Now, here's the good news. If I have a model like this, if my prior on f is a Gaussian process, and my likelihood function here is given by Gaussian distribution, then my posterior on f is also a Gaussian process. So what do I mean? I mean this is another conjugacy result. This is saying that P of f given D is proportional to P of D given f, P of f. So if this is a Gaussian process, and this is a Gaussian, then this is a Gaussian process. Okay? So it turns out that means my calculations are going to be very, very simple in this case. So, yeah?
So to do this, we have to basically choose a function that would define the variance, right?
The covariance function, yes.
Yeah. So my question is here, doesn't that mean that we basically have to either eyeball what function to use or test different functions?
Yeah, it's a very good question. The covariance function, the reason I chose the symbol k for covariance function is because it's equivalent to the kernel that's used in kernel machines, like support vector machines. And it's true that different covariance functions will give you different predictions, just like different kernels in a support vector machine will give you different predictions. In a few slides, I will talk about how to learn the covariance function directly from the data. So what I've described here is, imagine you gave it the covariance function. How would it make predictions? One argument I'll make is that it doesn't matter so much whether you have the right covariance function or not. We'll see that in a minute.
Are we making the covariance function a hyperparameter?
There'll be parameters in the covariance function that will be hyperparameters we can learn from the data. Okay, so let's actually look at these predictions. Okay. All right, so here is the demo I'd like us to focus on now. This is a situation where we have a bunch of data, and this data are pairs of x's and y's. Okay, and we want to learn a function from this data. Okay, so now I'm going to use just exactly the covariance functions from before. So let's just use the first covariance function. I'm going to choose that smooth, what's called the squared exponential covariance function with length scale 4. And here are the predictions. Okay, so the predictions here are shown as the mean of the Gaussian process, the posterior. Now, what I showed you at the beginning was samples from the prior Gaussian process. Now what I'm showing you are the mean and the variance of the posterior Gaussian process. Okay, the mean is the center line, and I think this is 2 standard deviation error bars on the predictions. So what you can see is essentially that given the data, all those crazy functions go away, and only the functions that that are somehow good at predicting the data survive. And so the posterior Gaussian process will look like this. Now, I could do the same thing for the slightly shorter length scale. And that's the predictions that I get if I use the shorter length scale, which again seem reasonable. They have slightly bigger error bars in some places, but nothing alarming. And now let me just use the longer length scale. these are the predictions from the longer length scale. So I had 3 different priors. This is, again, it's a bit like the 2 learners with the Bernoulli coin tosses situation. I started with 3 different priors. I condition on the same data. These are the predictions that I'm getting with those 3 different priors on the data. And what you can see is it's a little bit messy, but if you can follow the greenish lines, this I'll follow it with my finger, or actually with the laser pointer here. That's the prediction with the long length scale. It's smoothing a little more. And the orange line is the prediction with the shorter length scale. It's a bit more wiggly, right? But, you know, they're all reasonable predictions, right? Because they're all conditioned on the same data. So let's clear these plots. What about the linear Gaussian process? What predictions does the linear Gaussian process make? What do you think?
Somewhere from the upper.
Going down, you think? Okay, let's see. Yep, those are the predictions of the linear Gaussian process. Okay. Again, it's about as good as a linear, function is going to be able to do on that data. What about the Brownian motion Gaussian process? Let's just try that. Okay, this is interesting. Here's the Brownian motion Gaussian process. Now, it looks ugly, right? Because the error bars are jumping all over the place, but the mean is quite sensible, right? It's actually effectively almost interpolating the data, right? So even though it looks ugly, it's still, under that prior, this is a reasonable way of predicting from this data. We could argue it's overfitting a little bit because that prior doesn't have any smoothness in it. And you can see that in the error bars, they shoot up between every pair of data points, right? Okay. So again, I just want to make sure there's no mystery here. Okay. This is the MATLAB function for what I was just running. Most of this is just interface, which covariance function to use, blah, blah, blah. This creates the covariance functions for the different choices up to here. So where is it actually doing the Gaussian process prediction? Well, now it's plotting the answer. So actually, it's this bit of code here. Basically, that's the whole Gaussian process prediction. Once you've created the covariance function, then it's just essentially, and this is a really bad, I've just commented myself, it's a very inefficient way of solving this, but it's easy to understand. It's just, in fact, that equation there, that one line of MATLAB, is a prediction from the Gaussian process. Okay. So even though you're dealing with an infinite dimensional object, the predictions are very, very simple to compute, and they end up being, quite reasonable. Okay. So maybe we can take a break now.